Hey guys, so this is section 6.10. We're going to talk about equilibrium involving ideal gases and solid or liquid phases. And we'll use this as an example, the thermal decomposition of calcium carbonate into calcium oxide and carbon dioxide gas. All right, so what we know, one of the things we know is that the difference in the chemical potential, the change in the chemical potential, it's some of the moles of each species times its chemical potential, and that has to add up to be equal to 0 at equilibrium. Delta G is equal to 0 at equilibrium, same thing. So writing that out explicitly for this reaction here, the chemical potential at equilibrium of calcium oxide, the product, at whatever pressure is, plus the chemical potential at equilibrium of carbon dioxide gas at whatever the pressure is, minus the chemical potential at equilibrium of calcium carbonate at whatever the pressure is, has to equal 0 at equilibrium. The pressure will not be the standard pressure of 1 bar, so that means we need to incorporate the pressure dependence of everything involved. But, okay, we know that the chemical potential at equilibrium of calcium carbonate solid, that pressure, is going to be very, very close to the chemical potential under standard conditions of calcium carbonate. In other words, the chemical potential does not depend very much at all on of a solid or a liquid. It does not depend very much at all upon the pressure at which the reaction is taking place. Within reason, if you get really high pressures or vacuum, then it kind of changes. Likewise for calcium oxide. But for the gas, the carbon dioxide gas, we already saw back in section 6.5 that the chemical potential at equilibrium of a gas is equal to the chemical potential of that gas at standard conditions plus RT ln, the partial pressure of that gas over the standard pressure of 1 bar. Plugging that in to that equation we had just a minute ago, we get the chemical potential, using this and this for calcium oxide and this whole thing for carbon dioxide, we get the chemical potential of calcium oxide plus carbon dioxide, which includes the natural term, minus the chemical potential of calcium carbonate, has to add up to equal to 0. Rearranging this guy a little bit, bringing this on the other side, we see that the difference in the chemical potentials at standard conditions equals negative RT ln partial pressure of the gas over the standard pressure. That's this. But we also know that delta G under standard conditions is equal to the difference in the chemical potentials, products minus reactants, which is this term right here. So that tells us that we know that delta G under standard conditions is equal to negative RT ln of the partial pressure of carbon dioxide over the standard pressure. But we saw earlier that delta G at standard conditions is equal to negative RT ln Kp, which means that because these two are the same, that Kp must be equal to partial pressure of CO2 of the gas divided by the standard pressure. In other words, the takeaway from this, guys, is that the Kp does not include any information at all about the solids or liquids, just the gases. It doesn't. The solids and liquids do not affect Kp. On the other hand, if you're calculating delta G, you would definitely have to take into account the chemical potentials of the solids and any liquids. So let's do an example. We want to calculate the equilibrium pressure of carbon dioxide gas for that same reaction at 1159 K. Same reaction here, and you can find these numbers. So I'm giving them to you: the delta G of reaction and the delta H of reaction. Just so you guys know, the way you would normally find these is you would go look up the delta G and the delta H of formation of the products and the reactants, and just products minus reactants. Right? That would be delta G of the reaction. So what we're going to do is we're going to use the equation we developed in section 6.9, which looks like this: natural log of Kp at Tf is equal to natural log of Kp at 298.15 plus delta H over R 1 over 298.15 minus 1 over Tf. So let's get the ln of Kp at 298.15 first. To do that, we're just going to use that equation that we just saw. here. And because we know delta G, right? So plug in delta G over RT, get ln of Kp, which is equal to, ends up, again, as always, please check my math. I got natural log of Kp is negative 52.888. So now we can use that right here in place of this term, and then plug in delta H that we figured out from our heats of formation over R times 1 over 298.15 minus 1 over 1159. And I came up with, again, check my math, 0.5976 or so, which means that Kp, is equal to E to that power, which is 1.818 or so. But Kp is partial pressure of carbon dioxide over 1 bar, which means that the partial pressure of carbon dioxide at that temperature from that reaction is 1.818 bar.